Hi, shorter video on this one. You've seen this before, language of the orbitals. You've been using this for since you've been able to walk in chemistry. So principal quantum number, orbital quantum numbers, magnetic quantum numbers. So the language, principal. So think about what this represents. H psi equals E psi. There are only so many different energy states that you can have. So 1s, 2s, 2p, 3s, and so on. As you go up in energy state, or you go up in principal quantum number, you're going to have different types of energies, as well as the different shapes, the p's, the s, the d's. All of that originates from specific wave functions that will yield energies that match that match the energies that you have for the system. Okay, so the code and the periodicity, so this is where the periodic table's brilliance comes in, comes out of the systematic increase of these integer values that represent each individual function that represents the restrictions of the electron bound to that proton. Cool? So now what happens is you've got a way to link or see the similarities, or sorry, the connections between the different quantum numbers that yield from the solutions to the Schrodinger equation. Principle, 1, 2, 3. We designate these K, L, and M. Angular has two different ones, the orbital angular momentum and the magnetic angular momentum. You might be familiar with this, S, P, D, F. Graham probably told you all this in inorganic, but this one is known as sharp principle, diffuse, and then fundamental. Cool. So this originates from the aspects of the radial function. And then you've got m sub L going from minus L, 0 to positive L of whatever your angular momentum is. Think about the other thing. So we designate this as shells, and then these are subshells. So think about the connection of m sub L and L, okay? I've learned to optimize this board. Okay, so here I've got a diagram that we spent a lot of time looking at with the particle bound to a sphere. There was a reason that I was trying to get that into your brain while we're dealing with no potential energy. But now that we've added a potential, this becomes much more important. So the L value, so the vector here represents this L. It's not the magnitude or the length of the vector is L times L plus 1, all that times h bar, I believe. Nope, so all of that 1/2, there we go. Knew that didn't seem right, times h bar equals the length of the vector, and that's the so the length of the vector, and then that projection of that vector onto the z-axis has to be projected in units of 1, 0, minus 1, 2, minus 0, minus 2. And so there are certain angles that has to be. It can't be somewhere in between. Just like when you see that the electrons can exist in these energy states and they can't exist in between, angular momentum angles cannot exist in between L projected onto the z-axis in units of 1 or 0. It can't exist in that region, and that's called quantization of free space. Weird. It's trippy. Okay, that's just weird. That's a weird thing of quantum. You shouldn't be happy with it. I'm not happy with this. Why? I don't know why. I'm happy with this electron thing, but I'm not happy with this, like, it can only be here, here, or here. It can't be in between. It's an angle. It shouldn't matter. But it does. Okay, side notation. This is really cool. So here's a way that we notate this. So psi p0, p, this is telling us that L equals 1 and m sub L equals 0. So R is 2, 1, L, M sub L. So I went to the table and I wrote out the complete orbital. So there's your orbital. There's a wave function. Okay. So this, let's see if I can get this right. Here's a cosine theta, R cosine theta. So I'm going to take this out, R cosine theta. Okay. Now I'm simplifying this. This is a cool notation. Everything else, I'll use the red marker. Everything else, so that and that are going to go into this function, f as a function of r, because notice that's where all the r's are. Cool. Except this one. This one's going to stay out. Okay. So then what I can say is I know that the p orbital, again, we're in a p orbital, has 3 different directions. Okay, the p up, p middle, p down. Okay, well, p up, p middle, p that way. So psi p0 equals z times f of r. Psi p1 equals x f of r. Psi p minus 1 equals y f of r. Cool? Where this z equals r cosine theta. And that's a conversion from x, y, and z to spherical coordinates. So if we convert it back to Cartesian coordinates, through spherical coordinates, we get z, y, and x times a function f of r. Cool? Okay, bear with me for just a second. For the d orbital, okay, you get psi d m sub l equals, and we label this dxy, which is equal to x times y, our f of r function, dyz, which is equal to zy f of r function, and so on. You get dx squared minus y squared equals 1/2 x squared minus y squared f of r. Cool? So you kind of get the notation. I'm not asking you to do any of this notation. I'm about to show you something really cool. Okay. This comes from the conversion of spherical coordinates to Cartesian. This still has the radial component in it. That's your total orbital wave function. This is a way that we can denote which wave function we have. Cool? Okay. For those of you that took inorganic with Graham, please turn in either Atkins 9th edition or the 11th edition to the back, and you will find, let me find my 9th edition, the character tables. I'm on page 897 in the 11th, and I'm on page, wherever the character tables are, 943 and 945 on the 11th or 9th edition. So if you go to any number of the character tables and you see xy, zy, x squared minus y squared in the 5th column or 6th, depending on your character. So if you go to C2V, that's everybody's favorite, the group C2V, cool. You see z squared, x squared, y squared, xy, x, zx. Cool? That's what those represent. It's based on the symmetry. Awesome? And what's really cool about this is all of group theory is really just a way to solve all of these orbitals to determine when the wave functions become orthogonal to one another. Because when they are orthogonal to one another, that sucker's 0. Go team. I thought y'all think that was cool. For those of you who've had inorganic, and if not, you have something to look forward to when you get into group theory. Cool. That's all for the language of the orbitals. We're getting more and more into using the quantum numbers. We will start kind of decrease using the large extended wave functions for representing our systems, but please become comfortable with the atomic quantum numbers. Soon we will add multiple electrons, which makes the atomic quantum numbers term symbols. Go team. Bye.